Section 8.2 deals with L'Hopitals Rule, which helps us to find a limit when we have an indeterminate form. Sometimes when you look at the limit of something, you get some different answers that we don't really know how to handle. 0 over 0, infinity over infinity. Sometimes you get infinity times 0 or infinity minus infinity. All of these guys are what's called an indeterminate form, which means we don't know much from what we've been given. So we have to do a little bit more math. There's a mathematician, his name was L'Hopital, and he came up with this really cool formula that works. It's really neat, and it allows us to find the limit of these different things when we get one of these indeterminate forms. So what we're going to look at is the first form, which talks about being 0 over 0. And you know, you can't divide by 0, okay? 1 divided by 0, we know that that's undefined. We are not changing what we think about that. But if we have 0 divided by 0, that's something else. This is indeterminate. Okay, so notice that there's a difference here. So as long as I can take the derivative of both functions, and as long as g doesn't equal 0 when I take its derivative, we can use what's called L'Hopitals Rule. So here we go. Estimate the limit graphically and use L'Hopitals Rule to find the limit. So according to our rule up here, we need to take the derivative of the top. So I'm just going to rewrite the top. I'm going to call it f of x. So that's going to be 1 plus x to the 1/2 minus 1. The derivative of that is 1/2 times 1 plus x to the negative 1/2. The derivative of 1 is 0. And I'm just going to clean this up just a little bit by saying that f prime of x is equal to 1 over 2 square roots of x, 1 plus x. Okay. G of x then would be the denominator. So if g of x equals x, then g prime of x equals 1. So basically the denominator becomes 1, and we're left with just sorting through with this guy, because it would be this guy over 1 according to L'Hopitals Rule. So instead of having the limit as x approaches 0 of all of this, I would have the limit as x approaches 0 of 1 over 2 times the square root of 1 plus x. So if I look at the graph of square root of 1 plus x minus 1 over x, it looks like at 0, which is where my limit is told, given to me to check, it looks like it's going to be a half. And if you'll notice, there is a limit there, because we approach 0 from the left, and as we approach 0 from the right, the y value, which is where that limit occurs, this y value in here is really what we're interested in. And it looks like it's going to be a half. Well, all we need to do now is take the 0 and put it into our new equation that we got from using L'Hopitals Rule. So I'll just come on the other side of that graph, and we're going to look at x approaches 0 of 1 over 2 times the square root of 1 plus x, which is going to be 1 over...
Is it a 1?
Yes. 2 times 1 plus 0, which would be a half. And that is what we discovered by looking at the graph. So using L'Hopitals Rule and looking at a graph, we can see that this limit's going to be 1/2. All right, so here we have L'Hopitals Rule again, where f is equal to a, which is f of a equals g of a equals 0. F and g are differentiable. Got an open interval. Now what we're saying is, look, instead of just evaluating those limits at a, we can actually look at the limit on both of these guys. So let's take the first one here, and the top equation would be 1 plus x to the 1/2 minus 1 minus x over 2. So the derivative of this would be 1/2 1 plus x to the negative 1/2 minus a half. Okay, g of x is equal to x squared. So the derivative of that is 2x. All right, so here's our situation. And what we're going to do is we're going to look at this limit again, and this time we're going to put our derivatives in. So this is f prime of x here. And in the top, I'm going to have 1/2 times 1 plus x to the negative 1/2 minus 1/2. And that's going to be over g. And g is 2x. So when I put 0 in for all of these, you'll notice that, remember, this is 1 plus x to the negative 1/2, okay? So that's in the denominator. So if I put 0 in for x, and 0 in for x, I wind up with 0 over 0 again. And if you don't believe me, check it out. 1 plus 0 is 0. The square root of that is 1. So I have 1/2 minus 1/2. Okay? No problem. What we'll do is we're going to take a derivative again. We'll take our derivative of our derivative. And when we do that, I'm going to wind up with an answer that I should be able to work with. Okay? So the derivative then of f prime, so f double prime, is negative 1/4 times 1 minus x to the negative 3/2. And then the derivative of 1/2 is 0. The second derivative of g is 2. So whatever answer we get, we're just going to simply divide that by 2. All right? No problem. We'll do the limit process again. I'm going to have, and I'm going to write it a little bit differently this time, 1 over 4 times 1 minus x to the 3/2 power. Okay? All divided by 2. So now when I substitute in the 0, what happens? I get 1 over 4 times 1 minus 0 to the 3/2 power. Well, that's just 1 to the 3/2 power. So that's 1/4 times 1 divided by 2, which is 1/8. So we had to take the derivative 2 times in this case, and that's not necessarily bad. It allowed us to find a way to get the limit by using derivatives. And so this is a little bit of a stronger version of L'Hopitals Rule. Okay, let's look at the limit now as x approaches 0 from the right of sine x over x squared. And when we plug 0 in here, the sine of 0 is 0. The 0 squared is 0, so we've got this indeterminate form. And what that means is we're going to have to take some derivatives, okay? Not a big deal. We're going to set it up so that we've got f of x equals sine x. And we're going to set it up so that g of x is equal to x squared. Deriving the sine of x gets me cosine of x. Deriving g of x gets me 2x, okay? So take the derivative of the top, derivative of the bottom, and then we're going to put them right back into the limiting process here. And when we do that, here's what we're going to get. We're going to get the limit of x approaching 0 from the right of cosine x over 2x. Now, believe it or not, we can actually do this one because when you put 0 in for cosine, you get 1. When you put 0 in for 2x, you get 0. Now, this is an undefined term, so we now have to look at and investigate just a little bit about our graph and what's going on. So as we get close to 0 from the right, which means close to 0 from the positive side of the number line, then what you have is a positive number on the top, less than 1, and a really small positive number on the bottom, greater than 1. And what you're going to end up with then is, as you look at this limit now, if you take the 0 part out and just look at the limit, so what is the y coordinate doing as x gets really, really, really close to 0? What you're going to see is that we're going to go to positive infinity, because if we look at, like, say, 0.0001, well, for the cosine part, the cosine of that is going to be a number that's that's really close to 1, okay? But if you do 2 times 0.0001, then that's going to be 0.0002. Well, 1 divided by 0.0002 is a pretty large number. So as we get closer to the x coordinate of 0, our graph increases and goes to infinity. Now, using these same tools that we did right here, we can also investigate the sine of x over x squared as x approaches 0 from the left. And it's the same process. If I put 0 in here, I get 0 over 0, which I cannot have. That's an indeterminate form, okay? So what I'm going to do is I'm going to actually look at the limit as x approaches 0 from the left of cosine x over 2x. All right, now plug your zeros in. Well, again, 0 gets me 1 over 0, which is undefined, okay? So there's obviously something going on at 0 that I can't use. However, if we investigate what's going on as we get close to 0 from the negative side of the number line, things change a little bit. So if I let x equal negative 0.001, when I substitute that guy into cosine, I get the cosine of negative 0.0001, which again is going to be close to 1. Really, really, really close. When I put that same value in for x, negative 0.001, I get negative 0.0002. Well, large number on the top doesn't go past 1. It's below 1. Small number on the bottom, which means that when you multiply by its reciprocal, that's a big number. Well, I've got a positive divided by a negative. So in this case, that's going to take me to negative infinity. And if you're not sure what's going on, graph these guys. You can get a look at the graph on these guys and see exactly what's happening at the y, what y is doing as x approaches a specific number. Remember, with a limit, let's just have a real quick review. The limit as x approaches a of f of x. What we want to know is the y value we approach, okay, the y value we get close to as x gets close to a specific x value. So a limit we're looking for here is usually going to be a y value. All right? Here's another opportunity to investigate L'Hopitals Rule. And some things to remember are that the secant of x is equal to 1 over cosine x, and the tangent of x is equal to sine over cosine x. And here's the deal. The cosine of x is undefined, and the tangent of x is undefined when x equals pi over 2. So we have a situation here where we have to kind of investigate from one side or the other. And on both of these, if you come in from the left-hand side, so if we make this just approach pi over 2 from the left, then what happens is the secant goes to infinity and the bottom guy, tangent, goes to infinity, which is an indeterminate form. What we're going to do then is we're just going to take the derivative of both of these. So we'll let f of x equal secant x, and the derivative of secant x is secant x tan x. We'll let g of x equal 1 plus tan x. So the derivative of that is 0 plus secant squared x. Okay? And when you do that now, we can reorganize our fraction. And what you end up with when we use L'Hopitals Rule is you end up with your new secant x tan x over secant squared x. Okay, and now we can do some reducing of this guy. So this secant x goes away, the squared goes away. And remember, 1 over secant x is the same as cosine. So now what that's given us, let's see, I'm going to run into these guys. Let me get these guys out of the way. So I'm going to run into them. So now what we're going to end up with is tangent x, tangent x times cosine x, which is the same thing as sine x over cosine x times cosine x, which is the same thing as sine x. So just by doing a lot of algebra here, we can go from this guy right here, which is undefined on top, undefined on bottom, but clearly approaches a specific number, to our new problem, which says the limit as x approaches pi over 2 of the sine of x. Now you can plug pi over 2 in there, and you get 1. And that looks like what it should be. So L'Hopitals Rule to the rescue. It's a good thing. Okay. Now we've got the limit as x approaches infinity of natural log x over 2 square root of x. Well, what's going on in this guy is if you plug in infinity in, you get infinity over infinity. Okay. The natural log of a large number is a large number. Natural log of a square root is a large number. And if they keep getting bigger, those keep getting bigger. So let's break them up. We'll let f of x equal the natural log of x. So f prime of x is equal to 1 over x. G of x equals 2 square roots of x, which is, remember, this is the same thing as 2 times x to the 1/2. So the derivative of that is 1/2 times 2, or just 1, x to the negative 1/2, which is the same thing as 1 over square root x. So we can put in our new denominator in our new numerator. So let's get rid of infinity over infinity, and we'll have 1 over x over 1 over square root of x. And remember, when you multiply fractions, you divide by the reciprocal. So this is going to be 1 over x times x to the 1/2 over 1. Okay. One of the interesting things about this is if you have x over x to the 1/2 over x, you can subtract the exponents. And in the bottom, we get x to the 1/2 power. So what's happening? Well, we can set up our new limit. Our new limit will be the limit as x approaches infinity of 1 over the square root of x. And that's going to be 0. So again, using L'Hopitals Rule, we can reduce a really complicated fraction all the way down to where you let that top stand still, let the bottom grow, you get a number that approaches 0. Okay, here we go on these examples. They're a little bit different. Notice now we're looking at some limits here for the next two as x approaches positive infinity and as x approaches negative infinity. So when we work with these, what we want to do is use kind of a little bit of a different trick, and I'll show you what happens. But here's the thing. I've got the limit of x times sine 1 over x as x approaches infinity. What that's going to give us then is a situation where we get a number that gets smaller inside the sign. So the sign of 0 is going to be 0. And we have a situation where we're looking at x growing larger and larger. So we get the indeterminate form infinity times 0. And we can't have that. And there's really no fraction here to take a derivative of. So one thing that we can do that's basically an equality thing is we can rewrite this limit a little bit differently. And it's actually kind of cool how all this works. We're going to insert in here an h, and we're going to let h equal 1 over x. Okay? H equals 1 over x. So that means now that I have the limit, I don't have infinity anymore, but now I've got h, and as x gets, really large, h actually approaches 0. Okay, so, and again, we're going towards the right-hand side of this because we're talking about positive infinity. So I've got the sine of h. Now, also though, I've got this x right here all by himself. So what I need to do is solve this equation for x. And the one way that you do that is you multiply both sides by x. So that gets me xh equals 1, and then divide both sides by h. And we end up with x equals 1 over h. So now we put, whoops, not 1 over 2. What was that? Was crazy. 1 over h. So now we substitute in 1 over h right here. Well, what we're doing is we're looking at the limit as x approaches 0 from the right-hand side of the number line, from the positive side of the number line. Okay? And when we do that, 1 over h, as h gets close to 0, gets pretty big, right? But also sine h is interesting. So how do you deal with this? Well, go ahead and write it out like a fraction. We've got sine h over h. And again, as you plug in your zeros here, you get 0 over 0, which is indeterminate. So again, we went from 0 times infinity to 0 over 0. Take the derivative of the top and the bottom. F of x is going to equal sine h. G of x is going to equal h. So when you take the derivative of the sine, that derivative is going to be f prime of x equals cosine h, and g prime of x equals 1. And everything we're doing here, we can also do on this guy, by the way, because they're set up the exact same way. So now my new limit becomes the limit as h approaches 0 from the right of cosine h over 1. Now we can plug that 0 in, and we see that we're going to get 1 for our answer. Now, the thing with part 2 over here, as we approach negative infinity, we're now looking at the limit as h approaches 0 from the left, because we're on the negative side of the number line. But it's the same situation. We're going to end up with sine h over h. And again, we have to follow the same process and take the same derivative. So that's going to be cosine of h over 1, which is 1. So that's a really interesting problem, and we have to set up a pretty unique little inequality, which you don't have to do very often. But this guy right here is important to keep in your pocket because it still keeps our problem true. Okay, and we can use the properties of this to get to L'Hopital's rule so that we can find the limit. And if you graph this and look at it, you'll see that as x grows towards infinity, we do approach a specific number. So that this is how we would show that.